our first hands-on lab session. So hopefully by now, so the goal of this is going to be a very short lab session, and the idea is to just get CNTK set up on your machines that you'd be using and to get you started with using CNTK. We'll have more in-depth lab sessions later in the tutorial. Hopefully by now, all of you have the required downloads locally on your machine. So if you haven't already, please follow the instructions on this link to complete the setup. So by show of hands, how many of you already have completed the setup on your machines? Okay. How many of you would like more time to be able to finish the setup? Okay, so let's take about 5 minutes to finish the setup. So for those of you who have finished the setup, you can actually test whether the setup is complete by just running this simple logistic regression training recipe. Just use this command on the screen here, and if your setup was successful, you should see this output on the screen at the end of the log file. This page that has been lab setup, this link? Yeah. No, this isn't. So the way you can find this link is you can go to the, so either you can type it in if you're able to see it, or otherwise you could go to the KDD page for the tutorial, and there is a link to this page from there. Yes. Oh, sorry. So, okay, in the downloads, you would see a zip file saying, I don't know, CNTK. Let me find the name of the file. There's a zip file which says tutorial files or something. CNTK hands-on KDD 2016. Yes, CNTK hands-on KDD 2016.zip. Okay. So did you download from the USB stick or did you download it from here? From the web page. From the web page. So let me bring up the web page. So I think it's one of the last downloads in the list of downloads. Oh. It says tutorial files. Ah. Yes. Sorry, good question. Yes. On Mac, use a Docker. Run Linux in a Docker container and just then follow the instructions for Linux. Docker, I mean, I don't know if you have already run Docker. I think the instructions, the only thing I'd worry about is the download speed, but otherwise it should work pretty smoothly. But let me know if you run into issues. Give it a try. One other thing, make sure you install the right version of the binary. So for each platform, you would see there is a CPU-only version and there is a GPU version. Please do not use the GPU version if you do not have a CUDA-capable GPU on your machine, because those binaries have a dependency on NVIDIA drivers, and you can't install an NVIDIA driver if you don't have a CUDA-capable GPU, right? So use the CPU-only binary if you don't have a CUDA-capable GPU on your machine. Just out of curiosity, how many people have a CUDA-capable GPU on their laptop? Okay. That is impressive.
We have one. At least there is one.
please raise your hand if you run into any issue with the setup, and I'd be happy to stop by and, okay. The config file that you're running.
No machine network, I do big school.
Yes.
Did you just download it from the
Is this your folder?
Okay.
No, I mean big phone.
I mean my folder.
Can you quickly try something?
Yeah.
I got it.
Can you try the USB stick?
So which one should I install? Social ring. Where is the header and download?
So try copying the CNTK hands-on tutorial.zip file from here, and then try using that. I'm wondering if your download got screwed up somehow.
Oh, I don't think that's very likely.
Does anyone else need help with the setup?
Yes.
So I'll.
Oh, yeah.
Trying to run on Mac. This is the command you need to run. After installing Docker, run this command to start the Ubuntu image. I'll grab it later. Okay, so by show of hands, how many of you have been able to successfully run the logistic regression recipe by now? Okay, that's not bad. How many of you are still struggling? Okay. The Docker bit is, yes, it takes a little bit longer. How long is it taking to download the Docker image for Ubuntu? Was anyone able to finish it locally? Were you able to finish it locally, installing the Ubuntu image? Okay. Okay, so I guess we'll move on now. No, please continue trying to install. If you're still doing that, you definitely would be able to catch up when we move on to the later lab sessions. Okay, so by default, well, if you ran the, yes. Right. So it's in the zip file. If you use the, yes, so unzip that and there you would see this directory. Any more questions? Okay, so by default, so when you ran the logistic regression training recipe, by default the tool spews the output to standard error. But if you want to send it to a file, you can actually optionally use this command on the command line, and then it'll write all the log output to a file. Okay, so this is something Frank already covered. So sorry, this is not visible from here. Hopefully, you are able to look at the slides locally on your laptop. So we'll now take a closer look at the config file, which is basically used for driving the toolkit. So this config file has several sections. At the top, you have this setting called command, which contains the list of commands that will be executed when you run this config. For each of these commands, you should have a corresponding section in the config file that describes the settings for that particular command. So we have two commands here, a train model and test model. And the train LR model section is defined here. And this is a train action, which means that this command will define and train a neural network model. And then the test model here, the test model command is an eval action, and it will evaluate the trained neural network model from the previous command on a test data set. So now let's take a look inside the train config command. So here we have three main sections. The first section is the brain script network builder section, which is where you define the model and the network that you'd be training, right? And this is what Frank already covered. Here you specify things like the structure of the model that you are going to define and train. And then you specify things like what is the criterion to be used for optimizing the model parameters during training, and other things like what are the inputs, what are the feature inputs, the label inputs, and what is the evaluation criterion for this model. The second section in the train command is the SGD block, and this is configuring the settings for the SGD training procedure. So here you would see important hyperparameter settings like the learning rate to be used, the mini batch size to use during training, what is the size of an epoch, things like what is the training algorithm to be used, momentum versus AdaGrad. So these settings go in here. And the final section in the train block is the reader, which is how you configure CNTK to read training data. So here you specify things like what format your training data is in, which is CNTK text format in this case, and things like where to find the training data and what is the dimensionality of the various input data that would be produced by this reader. And then we have and finally we have the test model. And finally we have this test model section, which is just an evaluation section. So the only thing you specify here is the reader, how to configure the reader to read the test data. And this will evaluate the model that you trained in the previous step. So any questions on the config? Yes?
If my reader for the test data is essentially just the reader for the training data with the file exchange.
Okay.
How can I reuse that rather than just copy paste?
We have a problem with that today. So it ends up being duplicated today. With the Python APIs, it will be much simpler. And we are actually actively working on creating a solution for this. We realize this is a bit of a problem because you end up repeating information. So this is something we are addressing. Yeah. Okay, so now let's look at the contents of the log output, right? So when you ran the logistic regression training setup, the tool spewed a bunch of output on the console or in the log file, wherever you redirected it. So now let's look at the contents of the log file. So at the top of the log file, you'll see this header, which contains build information for the binary that was run. And this is useful for reporting bugs on the GitHub project. Further down in the log file, you'll see this section that says, which basically is a dump of the config with all the variables resolved. So CNTK configs allow you to define variables with values, and that allows you to actually reuse those variables inside dollar quotes in other parts of the config instead of repeating the literals again and again, right? So if you looked at this example, right here, for example, when we're defining the model, we're using these variables called label dim and feature dim inside dollar quotes. And this is just a means of not having to repeat the literal values again and again. So this is what is the dump of the config after all the variable values have been substituted. Further down in the log file, you'll find the validation output from the network, and this is perhaps one of the most important piece of information in the log output. What this is doing is this is showing you an entire dump of the network with tensor shapes of each of the operands of every operation in the network, right? So this is basically, this dump shows every node, and for every node it shows the tensor shapes for the input operands and the output of that operation. And if you somehow made a mistake in defining the shapes of the operands when you're defining the model, this is where it'll detect that and throw an error, right? So for example, if you're doing a times operation, you're multiplying one matrix with a vector, and if the dimensions of the matrix and the vector don't match, this is where it'll complain about it. And we'll have a small exercise later in the lab to look at that. The next section, this is advanced output. It shows how the memory sharing is applied across multiple layers. And this is mostly not needed unless you want to figure out how much memory is being used by your model and where it is being used. So this is kind of an advanced thing, mostly probably for CNTK developers to use. And the final output in the log file, at the bottom of the log, you would see the actual training progress. And here it shows at the end of each epoch, what is the current training loss value, what is the average training loss value for samples at that current state, and what is the average evaluation criterion value for samples used in that epoch. So you'd see values being printed for all. So we decided to run using 10 epochs, so you'd see 10 of these outputs at the end of the log file. Okay, any questions about the log output format? Yes?
It says here 4 out of 9 nodes do not share the mini-batch layer. What does it mean and should we worry about?
No. So you shouldn't be worried about it. The long answer, we should probably do this offline because this is, again, meant for CNTK developers. Hopefully, yes. Okay, so now we move on to our first task, our first exercise. So what I did is this logistic regression setup that we ran just now, I took that and I intentionally inserted an error in the model definition. And that is now available in the form of this broken.cntk.txt file. So now if you run this, you'd find an error that is reported in the log file. So the task is to read that log error and find out what is the error in the model definition that is causing this to happen and fix that error. Any questions about this task? Should I? So did anyone so far find the stupid mistake that this model definition has? Were you at least able to repro the log error? Okay.
Why is the folder called logistic regression?
So the name of the folder should be hands-on, hello world hands-on. So sorry, we forgot to change, we changed the name but forgot to update the slide. So it should be in the same directory where you ran the previous setup file. Anybody who's able to successfully identify the error, if you don't mind, please raise your hand and share your answer. Okay, so let's look at what the error is saying, right? The error is saying that the times operations, as I was saying earlier, when the network is being validated, it's trying to make sure that the shapes of the tensors are compatible, right, for each of the operands. So in this case, the operation which is having trouble is the times operation, which is a tensor multiplication operation or a matrix multiplication operation. So it's complaining, it also prints the actual dimensions of the operands, and it's actually complaining that the dimensions of the operands are not compatible. So the thing to do is to go back to the model file and see if you made a mistake in specifying the shapes of the operation. Yeah. So it's exchanged, so it's swapped, right? Okay, so I'll break the answer now. The error is basically, the error here is that the times operation that is being applied, which is this, even I'm having trouble seeing it, so hopefully you're following along in the slides. But the times operation where you are applying the time, a matrix multiplication on the feature input and the parameters of the weight, the parameters of the times operation. The shape of the times operate, let's say the shape of the parameters being used in the times operation does not match, because this is basically a matrix being multiplied with a vector, and the number of columns, columns of the matrix has to match the dimensionality of the feature input. So the mistake there is in this parameter tensor shape, it should be label dim colon feature dim, right? Because the number of columns should be the feature dimensionality, not the label dimensionality. Right? Any questions about that? Okay, so moving on to our final task in this session. This is just, right, so this model is super trivial and it does not make sense to run this in a distributed way. So the idea is to just go through the motions and show you how to run distributed training using CNTK. So running distributed training using CNTK is as simple as adding a few config settings related to parallel training and then launching multiple parallel workers using MPIs. So that's all, right? So this portion in the middle is what we are already doing. We add this additional setting to enable parallel training, and then we launch 2 parallel workers using MPI exec. And additionally, the few other additional settings that are already there in this config file up there, they select the parallelization method to use, which is 1-bit SGD in this case, with 1 bit of gradient quantization. Now, please run this command on the top and raise your hand if you encounter an error. It crashed, right? So the problem is this. So, okay, the problem here is that the CPU only build that you have does not contain the 1-bit feature. The 1-bit feature currently is only packaged with the GPU build. So the way to run your example successfully, go to the config file and change the gradient bits equals 1 setting to gradient bits equals 32. And then you would get the parallelization which most other toolkits have, right? Just exchanging gradients in their full 32-bit fidelity without any gradient quantization. So that should run successfully.
CUDA compute capability 3.0 hard limit?
Yes, and that is because of the use of cuDNN for convolution net. So it is a hard limit. Any questions about this task or any issues that you ran into besides the 1-bit not working with the CPU only build? Okay, so this is the end of this first lab session. Now we'll take a short 10-minute break. Okay, 5 minutes. We'll start in about 5 minutes, and we'd be hanging around. So if you have any questions, please feel free to stop by.
So I would like to, hold on, let me just change the setting. Okay. So I would like now to move on with a tutorial on real data. We're going to use the ATIS task for, the ATIS data for a simple spoken language understanding task. But before that, I want to go through one more time the brain script, so make it easier for you to understand what we're going to do. So you already saw some glimpses of that. The basic idea is that, well, when we have a neural network, we read a paper, we have a formula. And we need to translate that somehow into this internal computation network representation. That's basically the link that BrainScript provides. And there's two ways of doing that. One is you have a programming language API to build a graph. That's how many toolkits do it, and how we will also do it in about a month. And the other is a direct description, and this is the BrainScript approach that we had taken. And BrainScript is basically just a piece of text. You've already seen that. That can be either embedded in your config file, or it can be an external text file. So let's just look a little bit at the syntax. So BrainScripts always start with a record. Everything's a record, right? So you see the two curly braces, another one down there. And then you have assignments. So this one creates a record member called M, and it assigns it a value of 64. You can also have expressions that reference the existing members of the record. Now, this is kind of uninteresting because you somehow now need to start connecting this to the outside world. So one connection you need to make is to the reader. So what you do is you define what's called an input. And what you see here, in terms of syntax, input is an object that has a parameter that you construct it with. In this particular case, the parameter is M, so 64. And whenever we have these construction parameters, we use curly braces. That's sort of a convention that we're using. You could also use round parentheses, but this is sort of to show the intent. So let's define two more. Let's define a parameter tensor for what looks like a weight matrix and a bias. So, and now we can actually write a formula. Okay, so what does it mean? Well, you can read the formula, but what does it mean under the hood? It means that this constructs a piece of a graph. And this graph here consists of 3 nodes. It has a matrix multiplication, has a plus, and it has a sigmoid node. And then lastly, you need to say which of the nodes that you're defining there is the one that gets sort of output by the network. And in this case, I'm not training anything, I'm just outputting. So you define an output node. And in full setups, you will have criterion nodes and so on, like in the previous setup. Okay, so this is sort of the most basic, most simple BrainScript you could do. I think it's pretty clear, right? Or do you have any question on that? Okay. So now let's make it a bit more complicated. Let's put these weights, these parameters, into another record. Okay, so you have to give it a name. All right? So now you assign them to a record that has 2 members. And in order to access them, you see this down here, right? You now need to basically prefix it with the name of the variable that contains it. And the dot syntax here is used to pull out that particular element. Nothing unusual here. So we can also take this whole formula and move it in there. But if we move it in there, then we have a couple of things we need to change. So the params here obviously is now no longer correct. And we now need to access this somehow and assign it to prob. So now we call this model because it's more like a model than what we had before. So again, you define this. You have a record with 3 members. One of them is called P. And that's what you're accessing here and calling it prob. Okay. So now the next thing that you can do is you can parameterize these assignments. So that's typically called a function, right? So now we're defining something that actually takes sort of placeholders, and then these placeholders are what's going to be put in here. And when you invoke this, you also have to provide arguments for this. This is just a function, right? It's just like you would expect it. And then the one thing that is kind of a little bit tedious is if you always use these things and have to type .p here, it kind of doesn't make sense. You can directly put it here. But this is nothing, no special syntax. This is simply saying the result of this function is, well, it creates this record and then returns one of the members. It selects one of the members. So there's no special syntax or anything. And model here is just a function, a name that I chose. There's no magic about this particular name. There's a couple of magic names. So input is a magic name, parameter tensor is a magic name, and output nodes is a magic name. All of the other names are just chosen by me. Okay, so now we can take this one level further. I'm going to create a function object now. So, and why is this? This function here has a bit of a problem. It mixes the definition of parameters and the actual execution of this function. So every time you're calling this model function, you get a new set of parameters. And maybe that's not what you want. So Instead, we like to write it in this way. So instead of actually returning the value, we're returning another function. And so now this thing is basically, it's an object. So it's a function object. What is a function object? A function object is both a function and an object. It's an object in the sense that it contains data. And it's a function in the sense that you can just execute it. So the way to do that is first you create that function object, and then you can execute it, just like this. So what you get back here, this is now the function that you're executing. Okay? So, okay, and then the final thing that you need to do to connect this to the system is, well, this whole record has to go into this thing called the BrainScript Network Builder, and that is what you define inside the outer training block. You have seen this in the example before. Now, I would like to talk a bit more about this complicated way of defining first a function object and then a function. You don't need to do this, but it's recommended. And why is this? Because this is actually very handy. So for example, if you look at typical network structures, you have this sort of sequential form where you run through this. So they typically have this form. You have an x, you apply a function f, that would be this first network here. You apply another function g, that was the second, would be the second one, and another function h, and then you get out maybe this guy here or this guy here. So this is actually best described by simply saying, well, just run this function and this function and this function, and this is how you say that in BrainScript. Now, what is this colon? Colon, you will see this at different places. That's just an operator to construct arrays. Okay, so for example, if I write 1 colon 2 colon 3, that's an array of 3 elements, 1, 2, and 3. So this is an array of functions here. And then I pass this array to this thing called sequential, which creates or returns another function that executes f and g and h in sequence. Okay? So now I can invoke this, and if I write z equals f of x, it's actually going to execute f and g and h in sequence. Okay, and why is this useful? Well, now you can actually write your model in this form. And this looks already much, much, much more like your original network, right? Basically, every layer is represented by one line of text here, and it tells you exactly what you're doing. And it consists, every line consists of an object that you're constructing that represents basically this little gray rectangle here with its associated parameters. Okay, so this is what I wanted to just briefly review. This is the slide I showed you before. Do you have any questions at this point?
Actually a visual tool to create networks? Or?
We have a way of plotting the resulting network. We haven't prepared this for this tutorial. There is a command called plot, and it allows you to generate a file of a dot file that can then be visualized with the dot viewer. And I have some examples. I have actually a slide I could show you to you what it would look like. Do you want to see it? I can just give you a rough idea. So this is a network. The thing is, once you visualize a network that's a bit more complicated, it loses sort of value, right? So this is a network for a sequence-to-sequence model, and this has 600 nodes. This was described in a small number of pages in BrainScript, but you end up with a complicated network like that. So this is the problem. These visualization tools are kind of nice when you use toy examples, right? But once you go to real-life examples, I personally fail to see how this tells me too much. I think you can still zoom in and look at certain pieces, whether it got some things right, but it's hard to debug those things. Okay, so where were we? Okay, I think this is the slide.
So what should we do next?
Yeah, I'm going to move on to the next slide. This is the tutorial. Okay. Thanks for asking. Okay. So please, you have all installed everything. Okay. So what I would like you to do is I'm going to do the tutorial along a web page. So this tutorial and also the next one on image, we have prepared that as web pages. I'm pretty sure we will not be able to finish the image one. So you can basically also work through by yourself. So if you could please, for example, search for CNTK Wiki in Google or Bing. Take the first link, and then you click on tutorials. I'm going to do this for you. well. All right, and then you go to wiki, then you go to tutorials, down here. And this first, the second one here, language understanding with ATIS, that's the one that we're going to do. So if you click on that, could you let me know when you're at this point? Okay, good. Okay, so what I would like to do is, let's quickly, yeah, we have run everything. Okay, so what I would like to do here is I want to build a simple system for slot tagging. So I don't know if you're familiar with the ATIS corpus. The ATIS corpus, ATIS stands for Air Travel Information Services, and it is meant for developing a dialogue system that allows you to, ask questions about the flight data.
Go back again to go to guide us to this page.
Yeah, so you do CNTK wiki web search,
Yes.
then you go to the wiki link here, and then down here, that's where you see tutorials. It's on the sidebar. Sorry, you can't really see on the sidebar this getting started. On the right. And then the third one says tutorials. Yeah? Okay. Did you find it? Okay. Okay, so the ATIS task. So the corpus consists of queries. For example, show flights from Burbank to St. Louis. I'm going to make this a bit bigger. I think it's hard to read, right? So show flights from Burbank to St. Louis on Monday. And so what you see on the right here is what we should actually classify it into. So basically, we need to annotate which of the words have meaning and what kind of meaning. So this is supposed to say that, for example, Burbank is a from location as a city name. And St. Louis is a to location, and Monday is a departure date. So this is the task, and we're trying to build a system that learns this. Now, what I show you here in this strange format, this is actually the way that you would pass the data into CNTK. Now, CNTK supports different kinds of input formats. For example, for images, you typically just give it, image files. We can read PNG files, JPEG files directly. You don't really need to do much. If you do speech, you use some of the typical formats that people would use in speech. But there's a generic format. We call this the CNTK text format. And this is the specific form that you see here. And these files are organized in columns. So the first column here is an ID column. This is a sequence ID. This is one part of the test set. So all these 19s here say these all belong to sequence 19 in the corpus. And the previous is 18, the next is 20, and so on. Then you see this column S0. That's how we named the column. This is your query. And then you see a column S2. This is your result. And then you see what it says here. This says 770:1. What does that mean? This is an encoding of a sparse vector that has a 1 at position 770. The next one is a 1 at position 429. So why 429? It turns out that the word flights is the 429th entry in the vocabulary. Okay, so this is what you see here. This column S0 is the one-hot encoding of your input. And here S2 is the one-hot encoding of the corresponding labels. You see the O label here means nothing here. It always happens to be index 128. You also see these hash signs here. So these are sort of comment columns. These are a column that has a name of hash is ignored by CNTK, but we include it here so it's easier for you as a reader to actually, as a user, to see whether everything went right. You don't actually need this. This is really to make sure you sort of get an idea on what's in this file. You also see another column here, S1, which assigns an intent. That's a general description of what kind of question you're asking. I'm not going to talk about the intents in the beginning. We're going to get there later. So in the tutorial now, we're going to use column S0 as query and S2 as the target. And we're going to build a neural network that tries to compute S2 from S0. Okay? Okay, so I'm going to scroll further. The network we're going to build is a recurrent neural network. Yeah, so at the bottom, you input your words. So I just unrolled it for you here for the purpose of showing it. This is run through an embedding. Then we run it through a unidirectional LSTM. The output of that, the hidden state, is then fed into a dense layer, which is then used to predict your output. Okay. So now, what does this network look like in CNTK? And I'm going to use the sequential description that I introduced earlier in the BrainScript talk. It's actually very, very simple. Right? So it says, well, it's a sequence of an embedding layer, a recurrent LSTM layer, and a dense layer. And for each of those, we give certain parameters. So this means the embedding will embed things in 150-dimensional vector. And recurrent LSTM says here the 300 means it has a hidden state dimension of 300.
300 nodes, right?
300 hidden nodes, correct. And you can see there are links.
Layer.
I'm sorry, what is it?
How many layers?
One.
Just one.
Just one. Yes, only one layer. If you want more, then you just duplicate that entry. Right? Then you get a second layer. And you can, if you want, you can read up. So we have growing documentation. So for example, if you go here, you will be able to find the corresponding definition of this layer. Okay, I'm not going to go through this right now, but you could find the definition of many of the things already properly documented.
Excuse me, I got a question.
Yeah.
Can you explain 300?
So the recurrent LSTM layer, the LSTM, you have to define what the dimensions of the matrices are in there, right? So a recurrent LSTM or an RNN has a transform or a matrix that takes an input dimension, output dimension, right? And the output would be, in this case, a 300-dimensional vector. And because it's an LSTM, there's going to be a second 300-dimensional vector, which is the cell. And these two 300-dimensional vectors are then fed back, so that means there's also going to be a 300 by 300 matrix for the hidden state and another 300 by 300 matrix for the cell. And all of this is automatically generated for you. So I'm going to do something to answer your question, which I actually didn't plan on. I'm going to show you what this looks like internally. So if you feel confused, then maybe just turn it out, tune it out. Okay, so source, script. Okay, so there's a file called cn.core.bs, and for that, so we can see here, this is, yeah, I wonder how to do this. Yeah, this should work, right? Yeah, okay, good. Where did we go? Hello? Yeah, okay. So you can see this is the definition. It's a little bit more complicated. It takes more than one parameter. It has a couple of additional parameters, for example, go backwards. And then it defines several things. It defines an LSTM block here. I can show you later what that is. And then it has an apply function. And the apply function basically operates on something called the LSTM state. And it also has what's called the previous state. And this previous hook here is a past value function call that I think it's, did I scroll it away? I'm sorry. What just happened? I think I just accidentally hit something here. Right, so this previous hook here, okay, there's several layers of indirection. Sorry about this, is not meant to be purely read. So this next HC or previous HC is nothing else but the past value call that you saw earlier in the introduction. So what this means is it basically applies a past value on the LSTM state, then it creates a previous state, and then with this it calls this LSTM function and gives it the new input and the previous state. And I can also show you what this LSTM block looks like. So this is the LSTM block, and if you're familiar with it, it looks probably very familiar. You have the various matrices here. You have a weight matrix from the input. You have a weight matrix for the hidden state. In this case, we also can have an auxiliary input for sequence-to-sequence for attention models. You have the people connections and possibly a projection. And then you see the apply function again. This apply function basically just implements the formula of the LSTM, which is what you see here. Okay? So does that answer your question? Sorry for the detail, but I think you get a flavor of what it looks like, right? Okay. Good. So these things, they're all defined in this file, so there's no real magic going on. It's just you're using these pre-built building blocks that we have already created for you. Okay, so what I would like to do now is I would quickly walk you through the corresponding configuration file. So we've done this a couple of times, so let's do this one more time. You define a command. In this case, we start with a command called train tagger, and then there's another one I've defined called test tagger. You, for example, can define path names like this. So the data dir would be the root dir, and the model dir would be root dir / models. That's where the models are going to be. And then you define the model path variable here. This is used by the STD block. And then we go into the actual network description here, or into the actual training block. So before we go into the brain script, I want to start with a reader. So this is the definition of the reader, right? It tells you to use this particular component. That's a CNTK text format reader. And it says it has 3 inputs called query, intent labels, and slot labels. And it says that internally in the file, these are called S0, S1, S2. And what's also important here is that they're declared as sparse, so the embedding is efficient. Now let's go on to the brain script. Now this is going to be the full brain script, not just these few lines. So see what we do is we define a couple of variables here. Then we define the model exactly as I described it, so an embedding layer, a recurrence layer, and a dense layer. Then we need to declare what the inputs are here. And the inputs here are one called query and the other is called slot labels. And these have to be the same names as in the reader. This is how they are found and match each other. Then we say, okay, what is your actual model application? So how does your model get applied to the inputs? So this is a model of query. That's what you're going to put in. And it returns, now what's Z here? So you saw the dense layer up here did not actually apply a nonlinearity. So this is actually a linear output where we are supposed to apply a softmax here. But it turns out that it's a bit more efficient if we don't do that, if we just drop the final softmax step and instead move that into the cross entropy operation directly. That saves a couple of operations. So we tend to do this. And also when you actually use inference, very often you don't really care about the true softmax value. You actually care about the input, which is very similar to a log probability, except it's not normalized. So for example, in speech recognition, that's what you would need. You won't actually add a softmax on top. Okay, so now you still define these two operations. Your cross entropy with softmax is your training criterion. And errors is sort of an error metric that it keeps tracking for you. And now the last thing you need to do is you need to connect this to the actual training system. And for the training system, you need to tell it, okay, what are the nodes that it needs to feed features and labels in? What are the training criteria? And that's the most important one. So the trainer will use this node to backpropagate the gradient into. So this CE, this is the variable that's going to be optimized. Then we have evaluation nodes. This will be tracked while we're actually running. It will print something in the log, but it's not going to use this to influence the models. And then if you want to use the model for inference at a later stage, you would use these, whatever is defined as output nodes here. Okay, so I would like to let you run this now. So you will need to type this command. And it's actually going to be slightly more complicated if you haven't set up your path. So I'm gonna run this. Okay, so okay, first, I'm sorry, I need to go into, please follow me. You need to go into the directory that has the data. There you see the SLU hands-on. And you will see these few files. You will not see the models folder yet. And you will see basically the SLU hands-on. This is the main config file that I just showed you. And there's the corresponding data files, and there's a couple of files with solutions to the tasks. So now I'm going to run this. I need to pick the correct version. I'm going to run CPU only for Windows. So please follow along if you haven't done this yet. I'm just going to run it once without any parameters. So you see this is the correct path. You're able to run this, right? Get to this point. Okay. So and then I say, okay, config equals SLU hands-on. So I'm going to run this now. Let's kick this off. What's going to happen? So there's a lot of spew. You've seen this before. CNTK is at times very chatty. A little bit too chatty for my taste. Now you see we're going into this validation section here. I don't think we really need to look at this in great detail now. Okay, now I'm going to go back. It is starting the training. So here, I just want to highlight, just pick a random one here, for example, is validating this variable here. You see these names are partially auto-generated. This is a plus operation of something probably related to the input gate, and another input gate here, and it's a 300 times a sequence. This is a sequence dimension, and a 300-dimensional constant that it's adding there, or a vector that doesn't have a sequence dimension. Okay, now you see a couple of more. I just scrolled away. I'm so sorry. What happened here? Yeah. Okay, so another thing you will see, it tells you a little bit statistics. It says, okay, this model has 700,000 parameters in 18 parameter nodes here, and it lists those nodes down here. Now, 700,000 parameters is nothing. The Skype translator model, for example, had 160 million parameters. So this is a factor of 250 smaller than a real-life task, and this is simply because we cannot run, these high-end tasks on laptops. Okay, so now you can see it has started. It finished epoch 1, and you can see it prints the CE criterion. It says that epoch 1 consists of 36,004 samples. On those samples, it measured the CE criterion and also an error count, in this case 13%. It also gives you some more information. For example, it says that it took 15 seconds to compute this, and that it saved a checkpoint model after it finished it. And then it continued. You can see the next iteration already has a much better error rate here. And I'm just going to let this run. This example runs for 8 epochs. And could you please also try to follow along and run this on your own machines?
Are you running this distributed or?
Not distributed. This is just local. Distribution is something we will, this is always sort of the last step that you do. So is everybody able to run this? Okay. How fast is it on your machines? Is it about the same, 15 seconds per epoch?
10 seconds or?
10? Okay, and you're running Linux on a Mac? Okay, nice. Okay, one more epoch to go. You see the error rate's already much better, 1.2. Okay, or 2 more epochs to go. Okay.
Question.
Yeah.
So in the input file,
Yeah.
you had your outputs were telling which node you wanted to be set for that target.
Correct.
And then you said in the configuration, you said sparse.
Yeah.
So other option, presumably dense.
The other option is not sparse, yes, is dense. And okay, so so if you think of what is an embedding, right? An embedding is for every word in your vocabulary, it's a dense vector, maybe a 300-dimensional vector that you would like to learn for that, and that vector represents the corresponding word. Now, how do you encode this in an efficient fashion? Or how do you write this in a nice way? So some toolkits have special operators that say maybe table lookup or something like that. So in CNTK, we try not to do that. We try to be a bit minimalist, and instead we express that as a matrix product. So if you encode your words as a one-hot vector, and your embedding matrix as just a matrix of columns, and each column is one of the embedding vectors. Now you multiply the two. You take the embedding matrix times your one-hot vector. What will happen? It will just pick out that particular column of that of the corresponding word, right? But this is obviously not very efficient if you have a 100,000 dimensional vector and you multiply with 99,999 zeros all the time, right? So if you instead use sparse representation, what you will get is that it will literally only pick up the one column there and not do anything else.
So I'm just trying to understand, if you picked not sparse, what would you do in your input file?
Okay, so there's several places where you declare sparse. So first is the data is described in your file, in this case, in sparse form. If you don't want to use sparse, you don't use this colon notation, but instead you put a dense vector there. Just put all the numbers. If you want to have a 300-dimensional vector, then you would put 300 numbers here, right? The second thing is, even if the file is stored in sparse, if you don't say sparse for the reader, it will still output it as a dense vector in some cases, you can do that. I mean, for small things, you don't really care. And the third thing you need to do is you also need to tell the network that it's sparse. Actually, I realize I have a bug in the system. In the example, you should have set sparse equals true for the input as well. I didn't do this and I didn't notice it because it doesn't matter for this small set. Sorry about that. Okay, so these 3 different stages where you have to declare things to be sparse. So let's look at the result. So we have finished the training. It has come up with a final training error rate of 0.98. And now it continues with this evaluation action. We had specified that. So it likes to validate. And you see, we get a final error rate of 2.449%. That's for a very, very simple system that we just built, and we described it with 3 lines of brain script. Okay, so what I would like to do now is to go through a couple of modifications of the network. And so the first modification is a bit of a problem. So I realized that most people here do not have GPUs, and the first task was going to be to add batch normalization. And for batch normalization, we do not have a CPU implementation because this was based on the cuDNN implementation. So I still would like to do the following. I still would like you to ask you to add this, but success for you would mean that you run up to the point where it says, sorry, batch normalization not supported on the CPU. I still want you to do this because this gives you an idea on how to modify config files. So the way to instantiate a batch normalization layer is with this. It's important to include this normalization time constant. So could you please just open the config file and insert a batch normalization layer before and after the recurrence. And I give you 3 minutes. Just try to get it to the point where it either runs or it says batch normalization not running on the CPU.
Should we let the SLU finish first?
Oh, it's still running for you? Okay.
It's queuing.
Where is it at approximately? Sorry?
6, that's over there.
Okay, it's nearly there.
It's
Yeah.
queuing.
Oh, I can show you another thing. You can also, how about you kill it, and we're going to evaluate accuracy on whatever you have to this point. So I will show you what this command looks like. So at the end, you can now override command equals, it's not going to look very good here, sorry, I put this on the next line here. So command equals was it eval tagger or test tagger? Test tagger, right? Yeah?
Can you suggest that you increase the font size?
Even bigger. Okay, I will try that.
The interesting bits are not hidden by the screens.
Yeah, font. Is this better? Okay. So I hope the layout didn't get screwed up. So you type command equals test tagger, and you also need to now tell it. You can override which model is actually using. So you're going to say models equals, and I think it was called just slu.cmf. This would be the final model. And you have run up to number 6, right? So if you just say .6, this is the checkpoint model that was written out after 6 iterations. So I can just run it on that one. And if you try the same command, I'm going to bring the command up right after it's finished. And then we can see whether you actually get the same accuracy. Okay, so and this is the command again, if you want to try that. So it's 2.68, so it's nearly there. Okay, and for everybody else, would you mind trying to add the batch normalization layer?
You said we added before the recurrent?
Before and after, yeah. Actually, if you don't have a GPU, it doesn't matter. I just want you to practice to add a layer. That's all. That's all. You can put it anywhere you want, actually.
This is a beautiful tool you built.
Thank you. Did you get it to work? Did you get to the error message?
Batch normalization training on CPU is not.
Perfect. So good. So let me just show you what the answer looks like. I mean, it's actually very simple, right? It's sorry, the solution. Here it is. So all you need to do, after I increase the font size, all you need to do is insert it here. And the one thing that you need to make sure is that you put this colon here at the end. If you don't do that, then you would get some strange syntax error. So if you got to this point, then you did it right. And I got the same error here. I'm going to switch to the GPU version now. 1-bit SGD. OK, let's let this run. And what we hopefully would expect from the batch normalization is that it will speed up convergence. And we should be able to see that. So I'm going to bring up the original result that we had here. So I'm sorry. Right. So this is the current result. I probably want to scale this a little bit. So you see it started off with, started off with 0.5 and an error rate of 8. If we compare that to what we had originally, it was an error rate of 13. So this is the effect of batch normalization that you're seeing here. And unfortunately, this is a bit hard to see here. So after the second iteration, it's at 0.11 instead of 0.17, and it got to an error rate of 2.3. So even if you don't have the GPU right now, when you go back and you try to run these kind of things, batch normalization is a very nice tool to have. And we're going to wait until we have the final number.
I got a question.
Yeah.
So, is that a word-to-vec type embedding or something else?
It's simply multiplying with a matrix. So it's literally storing a single vector for every word, and we're training that matrix as part of the process. It's just part of the backpropagation process that comes out.
But is this a kind of word-to-vec embedding?
It's, yeah, word-to-vec comes with its own training procedure, right? Typically you do word-to-vec beforehand and you train your model, your embedding, and then you use this for a different task, for example. In this case, it's just jointly trained. So embedding layer itself, well, how about I show you what the embedding layer looks like? It's actually, it's just there. Here's the embedding layer. All right, so all it does is, the apply function here is a matrix product. And again, it's a bit more complicated than it should be. Typically, this is just a matrix product here. And you specify a parameter tensor, just a matrix. And the matrix simply has, the output dimension times the input dimension. So all you do is you multiply that matrix with that one hot representation. And as part of the learning process, it will update those parameters to be optimal for the task, hopefully, and this is your embedding.
But you also have a recurrent layer with that as well? Or?
Correct. Yes, it trains everything jointly, right?
So you got the 150 and you got the recurrent.
Correct. Yes.
Side by side.
No, it's on top. So let me show you the network again. So this is the structure of the network, right? So and also going to give you the, okay. So the input is run through this embedding layer, which is nothing but a matrix product. It just multiplies this one hot vector with a matrix. But the matrix is a learnable parameter. And then it sends this to the LSTM. Right? And the LSTM has the special thing that over time it actually takes an input which is already embedded, and it takes an input which is its own output from the previous state, and also the cell that's in there. And then the output is passed on to the dense layer. This is, by the way, another nice example on, you see, 2 of these 3 layers have no temporal dependency or no horizontal dependency. So the embedding operation and the dense operation will be launched as single CUDA calls, and therefore will be very efficient. Whereas for the LSTM, we have to run this left to right. So the only thing we can parallelize there is if we have multiple sequences that we can pack into a single mini batch. Then for we can run the same time step across all those different sequences at once, but not more.
How can we use the embedding for other tasks?
If you want to train a model, if you have trained an embedding like this, there is a function to export a model parameter.
Oh, export.
So you can write it out into a text file, for example. And then you can load, that's basically the simplest format is just, rows of numbers, just plain ASCII text. And then you can load that ASCII text file somewhere else. You can also, if you already have pre-trained embeddings from somewhere else, you can also initialize every matrix, every of these parameter tensors in CNTK by giving it a file path, and it will load it from there instead of initializing it with a random initialization.
Do you have examples for these operations somewhere on the wiki?
Yes, so for the embedding, there is an...
Think of like first saving out a trained vector or a trained matrix and then loading it in the brains.
I think we have it in the issues somewhere. It's something we should... So we have this section on the wiki, How Do I? And that section at the moment has only one article. I plan to go through all the issues and populate that with all the questions that we have already answered for people. And then I think this should be there in a couple of days. I will take that as an action item to put a description on that. Okay, perfect. So let's see how our batch normalization training did. We're down to 2.3. Do you remember we started out with 2.449? So with the same number of iterations, the batch normalized one actually worked better than before. So wonderful. Now let's actually go back to, let's do another task. Now, here, task 2. So one of the problems is, if you think about it, that this network here predicts labels, and all it has access to is everything that's on the left of that word. So for example, the prediction that there's nothing here does not have any information of what the future words are. So this is kind of a dumb model, right? It can only predict things from the left. So what I would like to do in this next task is to give it a look ahead of one word. So what we're going to do is we're going to add an additional, we're going to give, for example, this column here also access to this next embedding here. And how we're going to do this, we're going to write a function that will take this value and stack these two values and stack them on top of each other. And I'm going to show you how to do that. So what you will have to do is write a brain script function. So this is the first brain script function that you should write by yourself. And it accepts one input. And then it computes the immediate future value of an input. You have seen we have seen already example of past value, and future value is sort of the opposite of that. So if you use this expression, you have to use exactly this. Future value of 0, comma, and then whatever your input is called, comma, default hidden activation equals 0. This expression gives you the next value compared to the one that you're actually processing. Once you have that, you need to splice them on top of each other. So this is this operation splice, and it takes two values separated by a colon, so it basically takes an array of inputs. So, want to give it a shot? If you run into any questions, let me know. Or are you already lost? No, should be okay. So what I would like you to do is open the corresponding config file that we had and add a new function, for example, right before model or inside. No, before, yes. That expresses this.